Lesson: Updating and retraining AI models post-deployment. Updating and retraining AI models post-deployment is a critical component of maintaining the relevance, accuracy, and efficiency of AI systems in a dynamic environment. AI models, once deployed, interact with real-world data that often differ from the training data, leading to potential degradation in performance over time. This degradation necessitates a systematic approach to updating and retraining to ensure models continue to meet operational objectives. The first step in updating and retraining AI models is monitoring model performance. Continuous monitoring allows for the detection of performance drifts, which occur when a model's accuracy or other metrics worsen over time. This can be due to changes in data distribution, known as data drift, or changes in the relationships between input and output variables, referred to as concept drift. Tools like TensorFlow model analysis and IBM Watson OpenScale provide capabilities to monitor models in production, offering insights into performance metrics and alerting users to significant deviations from expected behavior. Once performance issues are detected, the decision to update or retrain the model depends on the nature and extent of the drift. If the drift is minor, updating the model with incremental learning techniques may suffice. Incremental learning involves continually updating the model with new data without retraining it from scratch. Algorithms such as online learning or streaming algorithms like Hofting trees can be employed for this purpose. These methods are efficient and effective for handling large volumes of data without significant computational overhead. On the other hand, significant drifts may require retraining the model from scratch using a new dataset that reflects current data distributions. This process involves several steps, including data collection, pre-processing, feature engineering, and model training. Tools such as Apache Airflow or Kubeflow pipelines can automate these workflows, ensuring consistency and efficiency. Apache Airflow, for example, allows data scientists to create directed acyclic graphs that automate and orchestrate complex workflows, such as retraining machine learning models when new data is ingested. Data augmentation and synthetic data generation are critical in situations where obtaining new labeled data is challenging. Techniques using generative adversarial networks or data augmentation libraries, like albumentations, can generate additional training data to improve model robustness. These techniques are particularly useful in domains such as healthcare or finance, where labeled data is scarce or difficult to obtain. Moreover, updating and retraining models require careful management of the model lifecycle, including versioning and rollback capabilities. Model versioning ensures that changes to models are tracked and reversible in case of negative impacts on performance. Tools such as DVC and MLflow provide model versioning solutions that integrate seamlessly with existing machine learning workflows. MLflow, for example, allows tracking of experiments, versioning of models, and deployment management, thereby ensuring a comprehensive approach to model lifecycle management. In addition to technical tools and frameworks, understanding the business context and implications of model updates is crucial. Models should be aligned with business objectives, and updates should consider the operational impact. For instance, in recommendation systems, updating a model might influence customer interactions and business revenue. Therefore, conducting A/B testing or phased rollouts can mitigate risks associated with deploying new model versions. These strategies involve deploying the updated model to a subset of users to evaluate its performance against the current model before full-scale deployment. A real-world example of effective model updating and retraining is seen in e-commerce platforms like Amazon, which continuously update their recommendation systems to reflect changing user preferences and market trends. By leveraging real-time data and advanced machine learning techniques, Amazon ensures that its recommendations remain relevant and personalized, driving customer engagement and sales. Furthermore, ethical considerations should be at the forefront when updating AI models. As models learn from data, they can inadvertently perpetuate biases present in the data. Techniques such as fairness-aware machine learning and bias detection tools are essential to ensure that models are updated in a manner that promotes fairness and equity. Microsoft's Fairlearn and IBM's AI Fairness 360 are examples of toolkits that assist in detecting and mitigating bias in machine learning models. In conclusion, updating and retraining AI models post-deployment is a multifaceted process that combines technical rigor with strategic foresight. By leveraging monitoring tools, implementing incremental learning or full retraining strategies, managing model life cycles, and considering ethical implications, organizations can maintain the efficacy and relevance of their AI systems. This comprehensive approach ensures that AI models continue to deliver value and align with evolving business and societal needs.